Welcome to the OFSC Hazard 2020 webinar series. Today's presentation focuses on lift plans for mobile cranes. My name is Ralph Willson. I'm a Federal Safety Officer and I'll be hosting today's webinar. I'd like to begin by acknowledging the traditional custodians of country throughout Australia. I'd also like to pay my respects to the elders past, present and emerging. The format for today will see a quick introduction by me. I promise to be quick. I'll then hand over to our presenters for the substance of today's webinar, during which I'll facilitate questions and answers as time permits in breaks throughout the session. In contrast to previous webinars, today's session won't be focusing specifically on compliance with the OFSC criteria, although, as many of you would be aware, the issue of lift plans forms a key part of the audit criteria around mobile plant. The session today is an opportunity to hear from leaders in the field, and we'll be looking at interpretations of key terms to do with lift planning that are thrown around industry and putting a bit of context around those terms and interpretation of them. We'll also be looking at types of lift plans and features of both simple and detailed lift plans, and some examples and key issues in the eyes of the Crane Industry Council of Australia, or as many of us know them, CICA. CICA's been evaluating the current state of play with lift planning and also looking at some future initiatives, and they've agreed to share some of their knowledge and insight into the issue of lift planning with us today. To provide that insight, we're lucky enough to have both Brandon Hitch, the CEO of CICA. Also, we have Stuart Edwards. Stuart's a director of Edwards Heavy Lift. He's an engineer with extensive experience over the last 20 years in construction engineering, lifting, and heavy transport, and he regularly undertakes lift studies and lift reviews of some of the most complex lifting operations occurring throughout Australia. Without further ado, I'd like to hand you over to Brandon, who will in turn introduce Stuart at the appropriate junction.
Thank you, Ralph. Thank you, everyone. As we'd indicated, we're going to really talk about three different facets of lift planning today. The what, while it sounds probably less exciting and certainly isn't where the focus of our time will be spent today, understanding the terminology I think is an important thing, because within CICA, this is something we're wrestling with at this present time. So I hope that you'll indulge me today with what we talk about is a work in progress. It's meant to stimulate conversation, which hopefully will be addressed during the question and answer periods, but it'll also give you a little bit of, I'll call it a snapshot in where industry is currently at, as well as potential actions that we can take going forward. And again, in this context, work collaboratively to try to clarify things. So we'll go through the terminology. We'll then look at a few examples of simple and detailed lift plans. And then at that point in time, I'll hand over to Stuart, who is an expert in this field, or specializes in this area, on the real nuts and bolts of how lift plans are completed. If you're game enough to stay with us for the full hour and a half, I think you'll find some very helpful tips that Stuart has collated around what he has found in the industry out in the field. These aren't meant to be things that you have to have 20 years of lift planning experience to understand, but something you might be able to take away today just to be mindful of when you are seeing a lift plan for the first time, give you a bit of a head start. So in the terms here, I want to just highlight 5 different terms, and we'll address these a little bit different as we go. There's really lift study, design lift, engineered lift, lift plans, and lift procedures all seem to be bantered around in the field without a single point of description that gives any sort of clarity, because I think a lot of these will be used interchangeably. And that's why we wanted to spend a little bit of time talking about what our assumptions are for this presentation, so that you know when I refer to something as lift study, it may not be what you call it in your business, but it's for the sake of this presentation what we refer to it as. Additionally, we'll talk about what's on the horizon for even some of this clarification, as I mentioned before. So firstly, I want to reset the topic of lift study. I don't want to talk about lift studies as they might have historically been 10 years ago, where they were a glorified lift plan that included a lot of detail, and it was, you could almost consider the lift study as a lift report. These were historical ways of completing a lift study. What I want to talk about in the current state of play is the lift study being more of a methodology assessment. And I've got two examples here to try to highlight this stage of the process that's occurring. So many of you might host high-risk workshops. At the early stage of these high-risk workshops, you'll be evaluating the feasibility of different options for your lifting activities. Those constraints that may dictate which option you select could relate to site access. What's available on site for not only the crane to perform its work, but nearby obstructions? Is the site a postage stamp? Is there an area for a laydown area for the crane? All those things become considerations when you start looking at option A and B, or A, B, C, whatever it might be. Further to that, it's nice to have a design a lift planning for a crane that you hope to be available, but if it's not available, whether it's in country or off of another project, these become obvious constraints we have to manage around. So then there's the typical things we talk about, which would be the load, weight, and dimensions when we start talking about, the last area of what is the rated capacity, what's the crane capable of performing. There's no point in trying to select a crane that's available but doesn't have enough lift capacity to perform the lift, because obviously you'll need to adjust the lift load weights if crane availability is not feasible. So, and then related to that, the ground capacity, what's been prepared, what needs to be prepared, what kind of surface are you operating on, is it a suspended slab? All these things will dictate what choice you make in determining the flow-on effect of crane selection, lift, sequencing, things like that. And then subsequently, I know it says crane rated capacity and utilization. I'm not talking so much about what is the crane capable of doing, but you on your particular sites, your business may have selected a crane capacity limit or a threshold that you want to operate under. So that would be beyond the manufacturer's load charts, and that may steer a decision from a single crane to a dual crane lift. So I've got two examples here, again, just to further this thought. It's this notion of making a decision around the benefits and disadvantages of a single crane lift and the benefits and disadvantages of a dual crane lift. Just two simple variants. But I thought, and I'll show a video here in a second, when this video gets played, it's a demonstration of the option B dual crane lift that was performed in New South Wales. Our other presenter here, Stuart, was intimately involved in this. What I want you to think about in listening to the narration, obviously the animation's pretty impressive in and of itself, but when you listen to the narration of the site coordinator or site manager, you hear him talk about things that all contribute to lift planning. You hear him talk about crane interaction between the tower crane and the hydraulic boom crawler crane. You talk about slewing with the load between the two cranes. You talk about the hoist speeds, which relates to coordinating the motion and the load share between the two cranes. And you also hear him talking about the complexity of picking and carrying or traveling with the load suspended. And you also will hear him discuss the impacts of getting those things wrong and what he did for countermeasures for this project. So I'll just go to that video, we'll play that, and then we'll get into some of the details other.
With the LTR 1100 and the M2480D was challenging due to the difference in size and configuration and the difficulty in non-synchronized operation. The crawler had 15.3 metres of boom and the tower crane had 92.7 metres of boom out. The crawler had 5 parts of line with a substantially slower hoist speed to the tower crane's 2 parts of line. Communication was the key, and the secondary dogman checked the alignment of the tower crane boom and the hoist rope whilst the crawler picked and carried. This was critical to the operation as the crawler was at 90% of capacity, where a minor difference in alignment could have pulled the tower out of radius and side-loaded the boom.
And Stuart will go into more detail about this and how this is an important thing to consider. It's the actual side loading of the boom. When we talk about multiple crane lifting, it's more than, and I'll elaborate this slightly. That's a very critical area in the lift planning stages that it's understood. So I mentioned resetting the conversation around design lift as well. Design lifts, I want to set a baseline, I guess, in that design lifts are defined formally in Australian Standard 2550 Part 1. This is the definition. I put it in here not because I want to read this to you, but I think it highlights that through the course of our, I'll call it sloppiness or looseness of how we use terminology, the original intent of a design lift has been been lost in industry. Now design lift is synonymous with lift planning. If you go back to Australian Standards 2550 Part 1, it really centered around the need to make an adjustment on the crane to consider a extraordinary lift. And I just wanted to throw out, just for controversy a little bit, the notion of an extraordinary or temporary lifting operation. How many of you would consider extraordinary lifting being installing bridge beams or putting in concrete precast panels? These things are now commonplaces that we sometimes refer to the requirement of design lift, but it's not its real intent. I'm going to implore you to consider we stop using the term design lift, because it is a misnomer from its original intent. And to be fair as well, the Australian standards, we're in the process of reviewing this standard in particular, Part 2550 Part 1. The design lift definition will likely be revised to be more representative of what industry practice is, or potentially delete it altogether and really focus on things like lift planning, which is more commonplace and common vernacular these days. So the other term that gets kind of bounced around, synonymous with design lift, with lift studies, is this notion of an engineered lift. To add the confusion, I'm not trying to throw Australian standards under the bus in this talk, because CICA certainly is involved heavily in Australian standards, but I do want to highlight, if you're looking for standards to bring clarity, there is some concerns, there's some confusion to arise here. So engineered lift is not actually defined in any crane standard. It's only defined in a rigging standard for chain slings. When you read it, it reads just like the designed lift definition we just looked at a second ago. I think, again, this exacerbates the confusion, the problem. What we're hoping here today is to stimulate some conversation about how this might be clarified and resolved. It is important, though, I think, that we do make a place for engineered lifts. And why I bring that up is the designed lift definition in the previous slide does not actually mandate the need for an engineer. However, as you can see in these activities listed here, I would make the argument there are clear reasons when an engineer should be engaged. And it's not just to keep engineers employed, but to deal with particular activities that are beyond what's common in lift design and using cranes to their rated capacity. There's a space for this in what I'll refer to as the sharpening of the pencil, making sure you have your I's dotted and T's crossed when you're dealing with things like considering re-rating the crane, or you're dealing with rigging arrangements that have unknown or atypical forces brought through them. And Stuart will do a good job later in the presentation to highlight some of those forces where they may be acting on the equipment, that the rigging equipment that isn't always well understood or well accounted for. And then certainly the design of lift equipment itself would require an engineer and with the knowledge and education and experience to perform those designs. And then lastly, you'll hear me advocate that dual lift operations, as a summary, do not require an engineer. I'll advocate for that, but there are several multiple crane lifts, or in some instances dual lift applications, which again we'll have a great example of that today, where an engineer is essential for it to be managed properly, and that insight is unescapable. So what I want to spend most of the time talking about today is actually resetting the conversation. I might be using words here that don't line up with your existing company policies, but I'd ask that you would just consider this as a conversation, and hopefully the Q&A will enlighten some of these difficulties that you might have in what I'm saying. What I want to focus on, instead of design lift and engineered lifts and lift studies, is lift plans. And why I want to do that is that more and more these days, lift plans have become the mainstay, and they have become the summary for what is used in the field and also what is developed in the office to take to the field. And in many cases, they're the guiding light in lieu of design lift, engineered lifts, and lift studies. So what I propose to you today are looking at this in a manner that's kind of two halves: indirectly documented and directly documented, and then also within the directly documented, not always going to the full extreme of an engineered lift plan or engineered lift and subsequent lift plan developed by the engineer, but that there is a place for a simple lift plan. There is a place for a detailed lift plan done by non-engineers or engineers. I hope that this will give us a chance to talk through this. And the reason, additionally, to the Australian standards being revised is the option for the high-risk work licenses. They're under review. They're about to be kicked off later this year. Currently, crane operators and riggers that are licensed to perform the work don't have formal training and lift plans. And when David and I were talking about possibly holding this session, I thought it was a great opportunity for industry to work together to try to improve safety overall when some of these planets are aligning between the Australian standards and the high-risk work licenses, where we can complement the conversation around the training of the operators, the crane operators, the crane crew, the rigging and dogging, and also clean up what's 20 years old in the Australian standards. So the reason I broke it out in these 4 segments is because my hope, and this is just a philosophical graph, but it's a little bit of this an 80-20 principle, but it's also this principle of there's a very powerful line in a silly movie called the movie's called The Incredibles. One of the things that Flash, the son, said was, "Dad, if everyone is special, no one is special." That's a very good point, I think, to be made, and translate that point into lift planning. If we treat everything as an engineered lift, nothing gets the attention of an engineered lift when it's time to take that care and time to take that attention. What I'm imploring you to consider is that if we can push the capability of our workforce downstream into the high-risk work license holders, into simple lift planning, into detailed lift planning, then the engineers that are specialists in this field will not be inundated with things that are, forgive me for using the word, but trivial. They'll be able to have a greater focus on the the parts of the project that do require their attention, because the workload is being shared across the business, having this equipping of other means of determining lift operations. So that's what I'm looking at here, and why I was talking about looking at 4 different options. One that is managed by the crane crew themselves and the high-risk work license holder, and then looking into different stages of lift planning. We'll go through in the second section of this discussion what is content behind a simple lift plan, what is content behind a detailed lift plan. We will not be talking today about specific examples of engineered lifts, other than some of the examples that Stuart has been involved with to try to show you how something can be so elaborate and the care that's taken in preparing a lift plan. We really want to equip you with some basic understanding around simple lift plans and the content, detailed lift plans. I think that's the last slide before we go into the question and answer period. I just hope this hasn't been revolutionary to you, but you've understood that it's a start of a conversation. It's something that CICA is working on. We're trying to bring clarity back into industry so that from site to site, crane companies are clear what's being asked of them, and then by providing that clarity, they can better serve you as their clients to perform operations to the best of their ability with the information that you've requested, and certainly in a safe manner. So I'll hand back to you, Ralph. I think the next slide is the question and answer.
Thanks, Brandon. I suppose just to kick off the questions there, can you put in context some of the key differences between a simple and a detailed lift plan, just to give a bit of context around that differentiation you put there? I can appreciate the move into the engineered lift plan. We all know that they're about when do you need a lift plan. There's different codes. Queensland's very specific in that, and there's other information, but primarily we use a risk management approach in how to get that. By the way, don't mean to talk too much, but I loved your movie analogy. Very good in the risk management sphere. Not everything can be high risk, nor should it be. It's a good one there. But yeah, just a bit of context about those two, simple and detailed.
Coming back to your question, Ralph, about what's a simple versus detailed, the real differentiation for us, again, looking at that graph on the slide a second ago, we don't want the simple to be too onerous. So you'll obviously see less detail within the simple lift plan. I'll show some examples where we've almost amalgamated a pre-start form with a take 5 and elements of lift plan. The detailed lift plan doesn't have those pre-start take 5 risk assessment level. The aim of the simple is this is a lift plan that's done in the field and on site. It's most likely going to be done with a crane that's a single crane, single hook lift activity. It's not done with intricate CAD details. We've got a I'm only going to show you the first page of the simple lift plan form. It doesn't go through the detail around doing a hand sketch. And I think that's often overlooked or neglected in industry. The value of getting the crane crew to talk and just sketch it out. It visualizes what's about to happen, and things can arise in that conversation. The detailed lift plan will spend more time focusing on the impacts of a crane doing a series of sequenced events, and you'll see that we've broken out the detailed lift plan to consider what is the weight of the load, but also the capacity of the crane in that configuration, what's happening when the crane is slewing or traveling, and then lastly, what happens with that load in the crane when it comes to placing the load. So we're looking at things in the detailed lift plan that relate to interaction between one crane and two cranes, talking about some of these, and that's where we start using some of the multi-crane lift durations that are outlined in 2550, the typical 20%, 33%, and so forth. We've incorporated that in that, but then the other part of the detailed lift plan, it assumes some greater level of rigging arrangement. We have in that detailed lift plan a more thorough assessment of what rigging is required, certainly in the ranging of the lift, but also how does that weight of the rigging impact the capacity of the crane, or its ability to pick up the rigging and the load. Hopefully that scratches the surface, I guess, on the differences between the two, and we'll go through these in more detail in the next session.
Thanks, Brandon. There's one come through in regards to, is there any guidance on common descriptions between critical and non-critical? So I suppose this goes into critical and non-critical lift plans. This idea of simple lift plans, detailed lift plans, critical, non-critical. Is there any likelihood that the Australian standard is going to, you mentioned they're 10 years old for 2550 Part 1. Is this something that's being reviewed in that? And I know the Queensland Codes of Practice is currently being reviewed as well. Are they looking at this terminology change, or is this something that is likely to come from CICA as an internal document?
Yeah, look, I didn't talk about complex or critical. It's something that certain companies utilize. And in our next slide, we'll talk about maybe some lift matrix framework to consider. To answer your question about how it interfaces with the Queensland Code of Practice, the Australian standards, and more, I guess, at a higher level, the regulations in general. Lift procedures are what's called out in the Queensland Code of Practice. They're not called out in Australian standards. Lift plans are not currently called out in Australian standards or in the Queensland Code of Practice. What CICA is trying to do and have a conversation like we're having today, subsequent or flow on from today's conversation, is create a document that feeds from our extensive network of principal contractors, crane operators, the national pool that we are very fortunate to draw from, to try to bring some clarity behind this. I don't think, without being any disrespect, and I say this because you just heard me use words that I've chosen to define a certain way. The reality is all these other terms, whether it's critical lifting, whether it's complex lifting, all these things are terms that have been made up to suit a particular company's framework for risk management. Unless we have a conversation like today that can start steering to a way of some sort of commonality, I don't see that level of detail getting resolved by the Australian standards. My hope is that we can talk in Australian standards about what I mentioned before about simple and detailed and engineered, and we'll go from there. Again, maybe we're still talking about this in 2022.
Is there any specific requirements of lift plans and the frequency? If we're, say, doing a dual lift and it's done 8 to 10 times on a daily basis, how often do we need to reinvigorate the lift plan or do a lift plan? Is it fine to keep a lift plan going for a month at a time?
I think that previous graph, I might just go back to this graph here. The point of this was to keep people thinking. It's easier for people to mandate something versus use their brain. The reason to equip people with training to do simple lift plans, do detailed lift plans, is as much about knowing when to elevate it to a higher level of capability, as much as determining when the risk is mitigated by doing something to its worst case scenario. Like using Mohammed's example is a very common example. I certainly hear grief from members about asking the common sense pub test, if you will, around if you've designed for worst case, shouldn't that be sufficient if other conditions haven't changed? So if you're picking and placing multiple loads, even if you're picking and placing within existing crane setup, the crane's not changing its setup as far as its location, but you're picking and you've assessed the condition in a lift plan environment to its worst case scenario, whether that's the farthest radius or the furthest or the heaviest load, whatever that you've selected that scenario to be, given all other conditions to be less than that, the first cut should be sufficient and cascade through those other 10. The classic example is the sound barrier install. Even to a degree, you saw that in that video that was the animation, there was a repetitive load, even though the orientation of the load was changing each time. So I don't think the full level of investigation was completed each individual time, but it was done as a worst case and then kind of backfilled from there. And I think that the more we can get people to use some of that common sense, hopefully that'll mitigate the excess, which again makes things trivial. If you didn't like The Incredibles, think a different context. How many buzzards does a piece of mobile plant have? It has a slew buzzer, it has backup buzzer, it has a horn, it has. If you start creating so many buzzers or slight variations of each buzzer, you start getting lost in what it is. We've got to reset how overly cumbersome we've made something. And I will try to give some guidance related to when you might choose to do the lift planning in the next slide. So
yeah, we've got other questions coming up at different points, so if you can hold them over to those, that might be the best way. Keen to hear the next section, please, Brandon.
We are touching on some of the things that were raised in the conversations. I want to highlight here, this slide is meant to equip you or maybe ask you to evaluate your own tools that you have, or consider these if you haven't developed something like this. But I equally don't want to confuse this point that these three categories, high risk work license, crew leader, and lift supervisor, I'm not trying to tell you in today's conversation that these equate to indirect documented versus a simple versus an engineered lift plan. These are ideas to try to break down how you might engage with certain personnel to perform the lift plan. So within crew leader, you might be doing simple and detailed lift plans, or within lift supervisor, you might be doing simple, detailed, or engineered lift plans. So don't confuse those two, but I just want to bring up 5 points here that we've tried to work with our members, and this is based largely on an existing document from a member. And I think it's very smart in how it's been prepared, in that it shows levels of authorization. Don't make everything go to the top. That's that everything special part. The other part I want to bring up, number 2, is don't just make the trigger a crane capacity or a load. Either one of those, I think, are neglecting the balance between cranes have different capacities based on their size. Working to a limit within a limit may only be a 3-ton load, but you're at 100% capacity of that crane selected. So use the crane capacity, because the stability requirements for a 3-ton mobile crane is the same as the stability requirements for a 100-ton mobile crane. The standard's universal. The next point, number 3, is interaction between cranes. We will talk about this in more detail with Stuart's examples. I've already mentioned again the rigging arrangement. How complex is that rigging arrangement? And then subsequently, what happens with the load distribution? Is it something that's changing throughout the lift? Is it just something that's determined at the beginning? Those two things are, even though there might be 2 crane lifts, can be managed grossly differently. The last thing is the ground condition information is very important, but it also, I think, needs to be linked to load capacity. Very common example that's already been discussed is the Queensland Code of Practice. It has a threshold for when ground conditions and engagement with the geotech is required, and you may choose to have those thresholds in your lift planning decision matrix. Simple lift plans, we talked, or was asked earlier. As I mentioned, the simple lift plan really is meant to be, let's call it a 2-page document, with the second page being a sketch and any other identified hazards. So what I've tried to show here is how in this pre-lift checklist, we've got a combination of pre-start, take 5, and lift plan characteristics. I won't go through this in detail here because we'll do a worked example a little bit later. And just for noting as well, as part of this session, if any of you want copies of the simple lift plan, the lifting equipment register, or the detailed lift plan, we'll make those available. It just shows you some of the broad brush, the simple lift plan we'll look at. The other part of the simple lift plan, which I mentioned before, it really caters to a single crane lift. What you're looking at here is the total in the load that's intended to be lifted as well, to start with, that information, as well as the line pull capability of the crane, turns into what are we working to for rated capacity of the crane at its maximum radius. With a single crane lift, we are still looking at the scenario of the radius for picking the load and radius for setting down the load, but we've also included a condition that may not be encompassed by either one of those, which is a potential for a max radius. So in this simple 10 lines, you're trying to assess what is the weight that needs to be picked. That's our first question. What is the required capacity of the crane in that radius configuration? Is that enough to pick the load up that you'd like to pick up? That's as simple as it gets. It deals with talking with the crew on site to try to develop this and then come out and perform the lift. I'll ask a bit of a controversial question in this slide. When we use a simple lift plan, this idea of, and I'm asking the question more so from just relying on the high-risk work license holder to determine it. So I'm not saying this in the context of going from a detailed lift plan down to a simple lift plan. I'm talking about going up from a high-risk work license holder managing the rated capacity of the crane and the desired load to be picked to justify the need for a simple lift plan. First question to ask, does the risk level warrant it? Do your own internal policies say we need to perform a lift plan because of those 5 options that I raised before? I put in here the value of the load because the essence of the simple lift plan is to document the thought process to say you've accounted for, I would say, a general assessment of the situation. It's not the precision that a detailed lift plan will go through that we'll look at in a second, but it's a general review, which is why we are just saying what's the pick, what's the set radius, what's the maximum radius, are within rated capacity. That's the other part of it. Sorry, when I say risk level warrants, the percentage of capacity. It doesn't cover off things that are operating necessarily at the 90%, 95% capacity of the crane, because you want to have more detail around some of the rigging and so forth, but it is a good process. So would you use a simple lift plan to lift a person? And that can be something that you already know the answer to from within your business. But with what we've described, is there reason not to? Is a simple lift plan adequate? Is probably more to the question. If we look at triggers of lift planning, often lift plans are triggered by rated capacity or the weight of the load, as we said. Here's a quick graph, and I bring up this example of a tower crane because we can put to the side for the time being, or for at least the simple example, any sort of ground conditions with it being on starter legs. If you look only at workbox as a function of crane rated capacity, at the worst case scenario for this crane, you will only ever get to 23% of the rated capacity of the crane with a fully weighted workbox. So that workbox is 750 kilos. The rated capacity in its farthest radius, 70 meters, still has a capacity of over 4 times the workbox load. If we go to the next slide, I just done a quick example to try to convince you of the options and how we can cater to a lift plan for a workbox. So within that pre-lift checklist, we're talking about rigging methodology discussed. We're talking about the workbox being checked. We've got the reeving correct, which is related to the crane configuration in that instance. And then this lift plan that we'll go through in the lift details is confirmed. That's the radius that we're going to be working to. So if we just look at these numbers again, if you're picking up a workbox of 750 kilos, your line pull for that crane, this particular crane, is 3 ton. The pick radius might only be 15 meters. The set down radius might be 15 meters again, because you're bringing the workbox back to its previous location, but you're taking it, you're extending out, you're trolleying out to 30 meters to either reach something, a facade, maybe a chimney, whatever the scenario is. I'm not here to try to contemplate that, but the idea of going out to a further radius. So instead of saying at 15 meters, we're good for 12 ton, you need to look at that load chart again and say, okay, what actually is our capacity at 30 meters? At 30 meters, our capacity is still 9,100 kilos. In that condition, you're operating over 10 times the rated capacity of the crane for the weight of the workbox. In the Australian standards, it talks about using cranes with workboxes. When they've been selected to do that, it only requires a rated capacity of a 2-to-1 ratio. You're 5 times greater than the minimum requirement of the Australian standards if I try to bamboozle you with different ratios to confuse the matter. But I would make the argument that a simple lift plan, in the lift plan segment of this, obviously you might have different protocols with ensuring communication, having backups for communication, things that relate specifically to a work box. Those are ancillary to this lift plan, but they're actually setting up the crane and making sure the capacity of the crane is okay, and you've accounted for lift plan oriented activities. I think a simple lift plan is sufficient. I'll jump on to a dual crane lift, and I'll continue to attempt not to be too provocative, but I'll hopefully make you think a little bit. Whenever we talk about detailed lift plan, we always think of it because it's a multi-crane lift. Stuart will show us, and his, in my conversations with him, it's really been fortunate for me as well to see valid points he's made about we spend too much time just managing this simple equation on the screen here. F1, F2, and F3. So this is what often triggers a detailed lift plan, the load share. What this doesn't do in its simplicity is consider the factors of why that load share and subsequently the derating of the padding of the load share to see if the crane still has capacity. This becomes the point that most people focus on, and I think that we've lost the real benefit of going through the motions of performing a detailed lift plan, because there's more than just making sure you have F1 and F2 sufficiently carrying the load. And that's what we saw with that engineered lift with the hydraulic crawler and the Fabco tower crane, was just so many other intricate details with reeving arrangements, the slewing, the pick and carry, all those things. The detailed lift plan itself gives place to account for complex rigging arrangements that need to be specified, and as we'll see in a worked example, Stuart will show the contribution that these rigging arrangements can have in the rated capacity of the crane. That lift itself is symbolic of a dual crane lift. What I would ask you, and if you talk about the amount of rigmarole that is required in maybe your processes around a detailed lift plan or when that's triggered in your assessment, this picture is actually taken from this dual cranes, and yes, it's 2 pick and carry or 2 articulated cranes, so that raises flags potentially somewhere as well. But this was only lifted off of a transporter, and then it was set down before it was picked and moved after that. If we only deal with picking and then placing, and both booms are parallel, all these things that really are mitigating much of the risk associated with crane to crane interaction, it starts asking the question of, do we need to have that level of scrutiny for something that would happen very commonly? If it's not a tree, it can be a container. It's something that begs the question, again, this is meant to be a little bit provocative, a little bit thought-provoking, to stimulate where this could go and how we might better improve things like the Australian standards and the high-risk work license, or even the revision of the Queensland Code of Practice. So detailed lift plan, it talks about these 3 scenarios: the pick, the slew, the place. You can see also here there's one line item for rigging bill of materials where it says 0 and 0 is because that's fed automatically from a rigging register. So that information, the weights of all the shackles, slings, any sort of chains or snatch blocks, so on and so forth, are all part of that rigging BOM that gets pre-populated here. But then you also see here the load factors are automated, where you select the type of crane configuration, and in this scenario it can provide that load factor. So in doing that, it produces the net load across the 2 cranes to consider how that fits into the crane capacity. Once you've decided what the load is, now we're looking at how does that load in the stages of pick, slew, and place impact or relate to the rated capacity of the crane. So we're looking at what is the percentage rated, and that will change if you are taking load from one crane to another, if you're rotating a load. All those things are potentials for being different in each of those columns. The last part of this, again, you'll get more of a flavor for in a worked example, is the other contributing factors that we want to detail in this lift plan to a greater extent, and that's the consideration for the maxed out rigger load, ground bearing applied pressure, and bearing pressure that's allowed. There may be something in here that a stipulation for a wind speed. Those things are able to be documented in this more thorough or more detailed format than in a simple lift plan.
This is just a quick slide on what software there is available. We've seen the CICA lift data sheets, the simple and the detailed. So there are various manufacturer websites that provide planning tools A lot of them focus on outrigger loads. They're definitely the correct source to get the outrigger load from, even though some of these other softwares in the list may attempt to provide those outrigger loads, but they may be inaccurate, which I'll go through in a bit more detail. Then you have the fairly rapid type, run-of-the-mill type programs such as Crane Expert or 3dliftplan.com. Some of them do try to provide outrigger loads. There is sometimes discrepancies between what that software provides and also the Cranemax example below and what the manufacturer provides. So you need to be careful there. Do they provide drawings? Yes, they provide 3D drawings. The accuracy of those 3D drawings it's a very pretty picture and rapidly quick. For a very detailed lift plan, they're probably just lacking a little bit, but great for your everyday lift. Manufacturers such as Liebherr are trying to provide tools such as the Crane Planner 2.0. They provide 2D, 3D drawings. They provide OEM outrigger loads. Unfortunately, it only works for Liebherr products, and also it needs to be augmented. Those type of softwares are great for working out the crane capacity and some drawings, but don't really pull it together. And that's where the CICA lift data sheets are great at pulling all the different information together into one lift plan. Cranemax and Lift Planner are sort of run over the top of various CAD programs, and they're excellent for generating 3D drawings. Like I said, their accuracy in outrigger loads can be questionable at times, so you need to go back to another software from the manufacturer to get the outrigger loads in a lot of cases. Your other sort of animation type programs, and I think the animations are becoming a lot more efficient these days, and you'll probably see a lot more and more animations as technology gets better. And data sheets.
Thanks for that. There's been a couple of questions come through. One was in regards to ground conditions playing such a critical part in determining lifts. And in this case, it was a question from a civil construction company saying they typically automatically go to requiring lift plans simply based on ground condition requirements and needing to validate those. How do you think that fits into the simple higher order, and when we get engineers, when do we don't need an engineer? We've had a little bit of a description about the planning software, but can you describe, that's only giving one side of the story, isn't it?
It's very relevant to what was discussed at the last webinar around differing of terms, around allowable ground pressure versus peak ground pressure, ultimate ground pressure. And if geotech is being provided to, the site based on this contractor's requirement, then I think you can see that even the examples that Stuart showed where ground pressure is provided, the previous point, I guess, in the webinar addressed, a month and a half ago, was about the discrepancy in what information is being provided. If that's wrong, then it doesn't matter what lift plane you use. I think that you could still get away with a fair bit of just simple calculations. And certainly, again, it goes back to what is the requirement of the crane's capacity for those circumstances. And it probably fits into that conversation previously around 8 out of 10 lifts are very similar. Do we need to do it each time? If you've already catered to a pad for a much heavier lift, a ground condition that's been verified for maybe what would have been the engineered lift, you've covered your bases for subsequent lifts that might be less of a problem, assuming the ground condition hadn't changed. That's probably the caveat.
There was one other question about work boxes, and in regards to should we be erring on the philosophy of proving it safe rather than proving it unsafe, which I suppose links into, how do you think standard operating procedures fit into this as well? Should we be looking at checklists for things like lift box? I know that's an area where Safe Work Australia, in fact, provide that typical 2-page sheet. These are the checkpoints we should be going through before you're doing it. Do you think that they, on some occasions, can replace the need to go to a more complex lift plan?
100% agree with where you're going there, Ralph. And I mean, CICA's been involved with some international conversations around lifting of persons with mobile cranes, and that's exactly what we did. We applied the requirements in the Australian standards. We applied the European requirements and American requirements to develop a guide that is its own standalone checklist. To mandate a detailed lift plan in lieu of these other supplemental information, I don't think that's correct. What I was trying to convey was the content of a simple lift plan. When you're talking about a single crane lift, you can't have multiple crane lifts with a workbox. In a conventional sense, I won't say never, because I'm thinking of one right now, but when it was a handoff. But let's talk about the norm versus the peculiars. In a normal scenario, in the tower crane example is a perfect one where a workbox is being utilized multiple times, maybe a week. That simple lift plan that's assessed and completed, and then the checklist that is complementary to that, I think that's where it's best to sit, not try to make a more elaborate lift plan to deal with the lifting component of the risk associated with picking up a person. And there is, sorry, just to elaborate, you did mention Safe Work Australia. The most recent update to that kind of topic was done in Victoria in May this year. Many of you might be aware the historical, what was known as the workbox alert or the secondary brake alert in Victoria from 2009. That's subsequently been rescinded, and this new guidance on lifting persons with cranes has been produced, and it doesn't give a checklist. CICA's augmented that with a checklist that the Victorian Construction Safety Alliance and CICA collaborated on, but it removes the requirement for an aftermarket brake, which wasn't supported by manufacturers. It was actually opposed because of the potential interaction or misuse.
So load charts, I'll just quickly run through what to look for, and then Brandon's going to go through a simple example of how to read a load chart. Obviously radius, boom length and chart capacity, they're the main big ticket items you need to look at. Other considerations, however, correct serial number and model of crane. One company I worked for that owned 10 cranes that were the same model number, but obviously different serial numbers. And the difference in chart capacity between different serial numbers was about 10 tonnes. So there can be, obviously the factory was improving the crane as they made new serial numbers. So it can be quite important to get the correct serial number chart. Design registered in Australia. Now this is from the old Australian standard, 75% static and 66% pick and carry. Australia has now adopted the European standard. It's still a 75% static, but the centre of gravity is within 4-degree tipping line. It's a different method for determining the pick and carry rating, but it still roughly equates to the similar numbers. The correct crane configuration, counterweights, boom length, the outriggers, whether it's on rubber. There's some on rubber charts that are static charts, believe it or not, or they're pick and carry, whether the boom is pinned or unpinned. A lot of the modern all-terrain cranes have what's called a pinned boom. That means the boom can't telescope in and out under load. It actually gets locked in position. And the top right picture there is the ram, which only stays in the bottom part of the crane. So that's quite a trap for young players, where the sales brochure doesn't show anything about these pinning locations. Say, for example, for the same boom length, you could have 5 different extensions of these sections out in totally different capacities. So that's worth covering. Other configurations, the tracks are retracted, the superlift, different angles on the superlift, etc. The slew angle. Most modern cranes these days stick with a 360-degree chart, although there's still quite a few cranes on the market that have restricted slew charts. The deductibles. A lot of mobile cranes, the hook needs to be separately allowed for. If there's a fly stowed on the side of the crane, or catwalks, working at heights sort of things, they're all quite often deductibles from the crane. The other thing is support conditions. The Australian standard had 1% as how level the crane needed to be. As manufacturers have got more adventurous, they want to get more capacity out of their cranes, so particularly in the bigger crawler cranes, they're putting more and more restrictive requirements for the level. So, for example, 0.5%. I've seen one crane, the manufacturer requires 10 millimetres out of level in 10,000 millimetres. So that's billiard tables flat. The environment and whether interpolation is permitted or not. In general, interpolation, that is, if the capacity is at 5 metres and 6 metres, and you're actually lifting at 5.5, in general, that's not permitted unless specifically approved by the manufacturer. This is a photo of a crane that tipped over, and it was the cause of the incident was a combination of things. One was the side slope derating, the other was the load swing. This particular crane was picking up that cage and reversing and stopping. So as it stopped, the load swung and tipped the crane over. The other thing was the counterweights were on the front of the crane, but the operator told the computer that the counterweights were on the rear. After this incident, Workplace Health and Safety Queensland interviewed 40 crane operators. Of those 40 operators they interviewed, 38 did not know that there was a side slope derating for the cranes. They thought the computer did it for them automatically. And in this case, it's a manual calculation. And of the 2 that knew that there was a required derating for the side slope, none of them knew how to do it. So I'll pass over to Brandon just to go through this example.
Yeah, thanks, Stuart. I think those stats, even though we were here talking about lift planning, the stats that Stuart just conveyed of 38 out of 40 people not having a full understanding on how to do this warrants a quick discussion, a digression, because this information we're going to go through here today ends up only being one line item of a lift plan. No different than all those examples about the correct configuration and so forth that Stuart talked about. Knowing the right input to put in is only going to give you the best option for a correct answer. If it's garbage in, garbage out, we're not winning with performing a lift plan. So I'll just, I know it's going to be difficult to really get you to ponder because you don't have the load charts in front of you, but I want you to think about this example of center gravity loads 5 meters from the front bumper of the crane. The boom is 10 meters long. You're going to articulate at 40 degrees. And you're on a side slope of 0.68 degrees. And then the load you're going to be lifting, it's with a main hoist in a 4-part line or 4 falls configuration. So if you start looking at these 5 elements of the planning stage, where do you look for? The most common, and I'll show you the answer to this so you can see, but I don't want you to overlook the sake of the conversation we're having today is going to look very straightforward. But and as far as reaching the conclusion, when you see this to start with, how do you know how far away 5 meters is from the front bumper? FRANAs are based on a load chart that begins at the front axle, not the front bumper. You need to account for that. What is a 10 meter long boom doesn't tell you what the radius needs to be, because that boom will be used to keep the center of gravity of the load 5 meters away. So you've got to, again, calculate the radius with that boom length and so on and so forth. So I'll just go ahead and go to the worked answer so that you can kind of see the path that we took. Where you find this information is in multiple sources. So again, trying to maintain the quality of the data going to lift plan, you've got to start knowing that the front bumper is 700 mils away from the load chart 0 point for its radius calculation. First thing you got to look for is that it's 5.7 meter radius, approximate 6 meter radius. Most people would read that right away. And this can happen whether you're in the field or in an office and think you're working at a 5 meter radius. So instantaneously, you can see that little blue square. You are assuming you're at 6.5 ton capacity. The reality is you need to round up, again, using the fact that Stuart mentioned interpolation isn't allowed on these load charts. You need to be considering you're working at a 6 meter radius instead of a 5 meter radius, because the actual radius is 5.7 meters. Instantaneously, you go from a capacity of 6.5 to 5.25, but you have not considered the articulation of 40 degrees, which is the yellow box there at 4.5 ton or 4,500, that was shown here. If you're assuming 6,500 because you don't know how to read the load chart properly, or where it's the center where the radius begins or is measured from, let alone not knowing what the articulation angle could do to the capacity, you're already off by 30% between 6,500 and 4,500. Then you introduce side slope. None of the 40 knew how to read side slope, so even if the two of you that knew about it, you wouldn't know how to read the chart. That radius requires a 40% reduction in capacity. So you can see in the red at the bottom right-hand corner here, you start at 4,500 kilos. You need to reduce 40% of that. That takes you to 2,700. But as Stuart indicated, there are many things that contribute to the deductibles for the load. So 2,700, any number on this load chart, regardless of scenario, not the scenario we're talking about right now, but any scenario, these numbers on the load charts, the green lines and the yellow lines, you cannot pick up a load that weighs that exact number because it does not account for rigging. It doesn't account for the weight of the hook, all those deductions that Stuart mentioned before that need to be accounted for. So even if you load chart with the side slope contribution says you can pick up 2,700 kilos, you need to still have something to pick it up with, which is the hook block and the hook. So in this condition, the hook block weighs 125 kilos and the hook itself that attaches to the block weighs another 15 kilos. So all up, your maximum load capacity is 2,560 kilos or 2.56 ton. That number is what needs to go into the lift plan. That number becomes how you measure your capacity to the crane's rated capacity, the load lifted to the rated capacity. I just want to, again, take a step aside and look at what this option is because it is so common. I'll like to share this with you. This is something, again, CICA is working on how to release this as part of this lift planning workshop today to those that are participating and want to utilize this service. So a few years ago, CICA and Multiplex created this automated or instead of using the manual load charts that we just looked at, this is a setup that you can select the AT20 Frana using the winch, and then you can put in the boom length, select the radius. You still have to figure out it's 700 millimeters from the front bumper. With that information, you can put in the articulation, the side slope, and then it will output the allowable load. And what I want to highlight in that bottom right-hand corner is something that we've added to this software, which I hope the industry finds useful. Those 4 columns are the scenarios that could happen with that boom configuration, so the boom length and the radius. Too often, Stuart mentioned before, if you recall, a 360-degree chart. On a slewing crane, the modern cranes are now producing variable charts based on slew angle. And he's 100% correct that you're planning, when you're doing general planning in the simple lift plan option, you should be using the 360-degree chart, or at least be conscious that you're using a specific slew angle chart, because the slew angle chart will always give you a better capacity than the 360-degree chart. What we're trying to show here in this right-hand 3 columns of the purple, green, blue, and dark blue is any condition that could happen with that crane in that boom length and radius. If you've picked the load up and you're driving straight ahead, you have a capacity of 5.3 ton. But if you then articulate, as we saw on the table, it drops to 4.5 ton. However, introducing a side slope, maybe you're traveling through the job site, 3.1 ton is your capacity at straight ahead. And as we saw in the worked example, or this example, 2.7 ton is the maximum capacity, not including the deductions that crane is good for. What we hope to accomplish in presenting the information this way is when you're planning, even if you're in straight ahead, at 5.3 ton, you're also cognizant, or at least able to see how quickly that capacity falls off. I mean, we're talking 50% there to 2.7 if the driving scenario, whether it's articulation or side slope, changes. In doing that, you can plan your lift at 2.7 ton, even though you might be able to pick the load at 5.3 ton capacity. Again, just want to highlight this because it is such a common misconception.
The next 2 slides are just some key lift plan errors that I commonly see with lift plan reviews. The outrigger load provided, the CICA presentation provides quite a lot of detail about what loads to consider, because the software produces an outrigger load or a track load for a specific scenario, and it doesn't. You need to manually go through the steps of the lift to get the maximum, and the maximum may not be the actual lift that you think it is. The bulk mat structurally inadequate is becoming a little bit more common. The telescoping or luffing of the booms, making an assumption that the crane can telescope, or that, and it's when the crane is in luffing fly, that the main boom can be luffed. You know, the luffing fly configurations can have huge minimum radiuses. Luffing the boom is often not permitted, luffing of the main boom component. Deductibles, not allowing the correct deductibles, and also not being aware of minimum weights. Like some cranes, they require, for example, a minimum of a 10-ton hook, even though you sort of scratch your head and wonder why. There's obviously various reasons behind those minimum weights. And so selecting a lighter hook, for example, may not be acceptable. The tail swing, so looking out behind the crane, not just where you're looking, where you're lifting, and the wind surface area. On the rigging side of things, load stability, and I'll show a demonstration of that. Statically indeterminate arrangements, I'll also explain that in a bit more detail, what that means, but it's basically the load share may not be ideal because like a four-leg chair, if you stick a coin under one of them, it might be rocking on two legs. The lift point design, and in particular, not per se the actual structural design of the lift point itself, it's just that the lift point designer is not aware of these two other items, the load stability and statically indeterminate arrangements. The center of gravity, either not accurately determining it or some sort of calculation error, and D/D ratio, so just basically the bearing of slings on their connecting elements or on loads. That's another whole presentation. You just can't just connect shackles and slings up together and assume that they're compatible. Planning considerations, obviously clearance is an issue that needs to be calculated. These days with lift planning software out there, that's becoming a lot easier to calculate these sort of things accurately. The deflection needs to be considered. The hydraulic boom cranes do deflect a lot more than the lattice boom cranes. There are some funny scenarios where, say for example, a hydraulic boom crane lifting an aircon unit on the top of a building, the boom bent a bit like a banana. They can place the load onto the top of the roof of the building, but as the load is placed down and the boom straightens out, you might have a clearance issue. The boom heel pin location. So on this particular crane here is a crawler crane. The heel pin is where the boom pivots from at the bottom. It's in front of the center of slew and down below. On an all-terrain crane is behind the center of slew and up high. Quite often, the all-terrain cranes in close quarters have a much better clearance than the crawler cranes, but the crawler cranes have their advantages in, it's a lattice boom, it's a lot stronger boom. The head height, how high you need to lift the load. For beginners, it's very easy just to look at the chart and go, at X radius, I can lift a certain amount of load, but forget that you need a certain length of boom to be able to lift up and over things, including handrails, lights, or other obstructions, and also the allowable distance from the hook to the boom tip. So the hook can only go so close to the top of the boom of a crane. It can't go all the way up to the top. This is just an example of a head height sort of check. The mobile crane you can see is poking through a door shown in red, and this was all checked with a 3D point cloud scan of the site. And this vessel that needed to be lifted, over the operating floor, and the gantry crane, it needed a specialised lifting device. It's not really anything to do with the capacity of the crane that was complex about this lift. It's more about vertical geometric clearances. Other planning considerations, the tail swing, the minimum radius, the site access and egress, particularly on city sites with mobile cranes with dollies, where for axle loads, the boom needs to travel on a little trailer behind the crane. They can be some quite serious planning requirements. The space to actually build the crane, and any public areas or exclusion zones. That was a video of a load collapsing during it's being lifted. There are actually no rules as to when structural engineering is required for a load or certification. There are some sort of site-based or union-based rules, like cages more than 20 tonnes need structural certification is sort of like a common rule, but it really does come down to the judgment of the lift planner to determine, yes, does this need a structural certification. Never exceed the manufacturer allowable wind speeds. There's two parts to the wind speed. The load chart has a wind speed allowance, and some cranes that wind speed is consistent across the whole chart of the crane. Some cranes, the wind speed or allowable wind speed varies by boom length or crane configuration, and you need a detailed chart to find out that answer. Then the second part of that is that chart wind speed is based on a surface area of the load being 1 square metre per tonne. If you have a larger surface area than that, you need to reduce the permissible wind speed so that you have the same equivalent horizontal load to the crane. And this video is quite an old one. It's from, it's called Big Blue. There's a whole documentary about it. And I guess the root cause behind this incident, and 3 people died, was wind.
The unthinkable was about to happen.
What the hell is this? What's going on here? Okay, watch it, watch it!
CICA has a guidance note on how to calculate that, and most crane companies these days are now incorporating that as just 2 simple boxes in their lift plan of what the chart wind speed is, what the surface area of the load is, and its drag coefficient to calculate a permissible wind speed. The other aspect with wind, this was at Mecca. Several hundred people died, I believe. The crane was set up, left up overnight, and it was blown over. I regularly see cranes in city locations that have no space to lay the boom down for bad wind. And a lot of these cranes, the wind speed where you need to lay the boom down is 16 metres per second or so, which is not a large wind speed. So it does need to be included in your planning for the site. These are just some examples of rigging diagrams. First one looks complex, but probably, is probably sit in the, it's some pretty drawings, but generally it would sit in the sort of like detailed lift plan rather than engineered lift plan category. This one here, mainly because of the crane capacities above, but we had some quite fancy ways of redistributing load. So this one would fit in the engineered category. And you can see that multi-hole plate there that was assisting as part of that. Spreaders versus lifting beams. I would say once a week somewhere in Australia, a combination spreader lifting beam would be bent because of the misconception of what they do. This one here is an example. Snapped, they were lifting a 50-ton load. The data plate on the device itself was terrible. And if you didn't know what a spreader or a lifting beam was, you wouldn't know what the difference was. So, yeah, obviously they put 50 ton on something where it's good for 6.5 tons and snapped it. This is a combination beam that we designed, and the data plate on it has clear pictures to show the difference in capacities, and you can sort of see it's 3 tons versus 15 tons. So a lifting beam is in bending. A spreader spreads the load, so it's predominantly in compression. However, spreaders aren't just bending as compression members. This is an example from a pipe spreader design. If you took the compression load only, you could get away with a 273 by 6.4 CHS at an 89% capacity. When you take compression and bending into account, it's at 580% of capacity. So you need to go quite a few sizes up to get the correct pipe size. The average, I guess, design behind a spreader is that there's an included angle of 60 degrees above and plus or minus 5 degrees below. This is another common error. Let's say this is a 50-ton spreader. That means each end is good for 25 tons. So in this picture here, you can't lift a 50-ton load because probably 40 of it is on the left-hand side, which exceeds the 25-ton capacity. This is an example of a load that has an offset center of gravity. You can see there's the extra shackles on one side to move the hook of the crane over to achieve this load, and there's obviously heavier load down one side. And that spreader, well, that's a combination spreader lifting beam, had sufficient capacity for that. This is an example. The spreader has been used upside down. You can see this little lug pointing up. That's supposed to be pointing down. In that design, the compression is supposed to be acting on this neutral axis. In our case, it's acting above the neutral axis, inducing more bending. The other thing is if you have a big angle below the spreader, you induce additional compression, and that needs to be checked structurally. Load stability. So this one, I've got a scale model which I want to show you. If you imagine you have this load to be lifted and the lift plan has the load on the right hand side. However, when you get to site, they say, oh sorry, we don't have the spreader, we've got a lifting beam, it's structurally, it's got heaps of capacity, can we change it over? In this case, because the center of gravity is above the lift points, the answer is no. So I've seen this happen in real life and from a number of videos. So it's not something that's just theoretical. So this load here, if you can see, I've got it set up. The center of gravity is above the lift points, and I have my slings above. I can wobble it around and it's stable. Looks pretty good to me. If I change that to a lifting beam, the load just tips over. And what's happening is that as the center of gravity moves over, you can see the spreader tips over, which puts more load on one side and it keeps on rotating. A load with the lifting points above the center of gravity is stable. So you can see we have a sheave up the top here. It can let the rope run through. It's still stable. This case, where the dimension A is less than B, the load is unstable. This one, it's unstable because the rope can run through these wire ropes. This is an example of a lift plan, obviously quite detailed lift plan. Everything's okay technically as per the lift plan. However, up the top here at the hook, you can see the slings have been run over the top of the hook and back down again. So we're back to something similar to this sheave, and the load is unstable. Another example of this occurring on another site. In these two cases, they were very lucky because the friction of the sling on the hook and the center of gravity was not so high because there's a concrete or a lot of weight down low. So the friction versus the instability was meant that the load didn't tip over. But lucky to get away with it. This is another example, similar principle. This is something we designed, which I don't think I've seen too commonly elsewhere, where we had a limited head height, so we couldn't put lots of long slings above to match the center of gravity. So we achieved that by having a moment connection around this corner and the arms dropping down the side, and that worked quite successfully. Always be cautious if the lift points are below the center of gravity. This is quite a deep beam. So it's probably just lucky that it didn't tip out. The other aspect of load stability is this is a pile. The pivot point is down the bottom corner. As it rotates over, it will get to a point where it will want to stand up by itself because the center of gravity has gone past the pivot point, and that would give major shock loading to the crane. A better solution, you can see this orange block here, would be a two-stage rotation where it rotates where the center of gravity is behind that red line, engages onto the new block and continues its rotation past that pivot point there. This is another rotator design where the center of gravity or center line of the pile stays on the center line of rotation, so ensuring stability. So static indeterminacy, fancy word for the four-leg stool. If you stick it on the ground and the ground's a bit uneven, or you stick a coin under one, get a potential for the load to go across two of the legs. So in the rigging world, this is called any two legs in a multi-sling arrangement need to take the load. If it's a three-legged stool, if you stick the coin under the one leg, all three legs still touch the ground and they more or less still maintain their same load share, apart from any sort of geometrical change from it tilting over. I just want to show you an example, a whole presentation you could do about this. I have the same rigging arrangement here. We've got a spreader bar across the top. We also have what's called in the industry equalizing triangles. The center of gravity of this load is in the center. I haven't made any tricks here. You can see it's in the center here. I'm just going to set the scales to 0, and from all that equalization, we've got an equalizing triangles, we've got a spreader bar. We should be identifying the center of gravity of the load is in the middle. We should be identifying that the loads are the same. But not sure if you can see that there. 850 grams, 400 grams. Close to 400 grams there, and 800 grams there. So we have these two diagonally opposing ones taking 400, and these two diagonally opposing ones taking 800. The reason why this is occurring is the length of these slings is not exactly correct, which matches real life. The allowable tolerance of a sling is 3% of its nominal length. Then looking at this, I'm not sure if you can see this triangle here. This triangle has rotated a little bit because of the slightly different sling lengths. And because this side here is closer to the center line, it takes more load. So that needs to be taken into account, not just for the rigging arrangement, also for the lift points. It could be any variation of it. 4 slings in a line, 4 slings in a box pattern that I've shown there, etc. This is a detailed lift plan example, just to finish things up now. This is there's 23 pages. Trying to keep them condensed as possible is always my theory. A sign-on sheet at the front, a data sheet like the CICA one, a checklist, extracts from the charts that the operator can refer to, the load information. So basically this is showing that the load has been structurally approved for the way we're rigging it, a rigging diagram, and then some general arrangements. And finally, the applied bearing pressures and the allowable bearing pressures. This is just a picture of the actual lift itself. So you can see that the cranes, we've got the cranes moving so that at this critical stage where we're doing the tailing, the 2 booms are in line. So the side loads to the boom of the crane are minimised. The data sheet, we have the configuration of the crane at the top, its boom length, its configuration code, the hook details. So it's just the capacity of the hook. The hoist rope in this particular crane is not included in the chart capacity, so we allowed for the hoist rope. We're checking the total line pull and parts of line. So parts of line is how many times the hoist rope is reeved up on the hook, and similar for the other crane. The rigging, we're just going through a weight takeoff of the rigging and the weights. These are the attachments, typical sort of data showing pigtail and place. The interesting things you'll see here is the tailing for the main crane. We've only got a 1 factor, not a 1.2 for a multiple crane lift. And obviously there's some various control measures that we went into to determine that this was acceptable. The other interesting thing about this you may have picked up that halfway through the lift, the slings actually touch the side of the load. There's some engineered designed big round things that are sort of bared on. The interesting thing is at the start of the lift, the tailing crane gets 137 tonnes, but partway through the lift, the load actually increases to the tailing crane. The other thing that happens too is the center of gravity goes above the line of action between the lift points by 92 mils. So we need to have control of the load in the top main crane to stop it from tipping out sideways. And then when we get to this point, the load share changes again. So some quite detailed calculations, and you'd probably put this one, because of those elements, into the engineered lift category. Just a picture of the rigging that was used, bit of a plan view, general arrangement, pretty typical of what would be in a normal lift plan. Head height here, and just clearances and things like that. So yeah, thanks for your time, and I'll pass over to questions.
That's fantastic. Thanks for that. There was two questions that have come in that I thought I'd put to the group. One was in regards to you, particularly Brandon, and it asked, could you share your thoughts on dynamic load moment indicators for articulated pick and carry cranes? There are some companies that have mandated these. Any comments that you might have on that?
I think that the dynamic load indicator is a important advancement because it incorporates side slope, but I don't think it provides anything for lift planning, because it only tells you the current state. It doesn't tell you what's about to happen. It tells you what already happened or is happening. So to treat that as an alibi to, I think that, like many things, we talked about some of the artificial intelligence as well, maybe having a perverse outcome. I think that it alone is not your get out of jail free card. It's an advancement, it's an improvement, but it can't be seen as something that does anything more than tells you when you've got a change in circumstance. That's why I was trying to highlight in that lift planning, trying to show a more simplified version of the dynamic load indicator in the plan that says these are the potential capacities that might fluctuate through the use of an articulated crane. And that has its own limits, because all those things are based on an assumption of 5-degree slope or less. So if you go into side slope that's more than 5 degrees, well, all bets, you can't use that chart anyway. And I think that's probably my only criticism. I think it's in that you heard Stuart, as I've said before, about the 360-degree chart. Same principle with slewing cranes. The dynamic capacity that they give is great, but if you rely on that to be the new capacity everywhere, you'll find yourself in overload condition or higher capacity utilization than you maybe have intended in a different slew angle. So I'm curious, Stuart, do you have a different view or your thoughts on that, if you have any thoughts?
I guess I just expand on your point about it's telling you what is happening now. Like there is a trend to do these dry runs with the crane, because there's no charts from the manufacturer but the problem is it doesn't take into account the second order effects. So when you do your dry run down a side slope or whatever, and then you do it with the crane, there's tire flex, there's boom flex, there's load swing, there's all sorts of things that multiply, or in the event of an incident, can multiply loads very quickly and rapidly that that dry run has not picked up and will never pick up.
The critical thing is coming back to that education piece. Like in the June presentation of Fulton Hogan, they talked about the elaborate training they provide, and CICA has materials for that if that's of interest. They are fairly dated, but the physics are still the physics. The understanding what's going to happen, and even those second order effects like Stuart mentioned, are important for the operator to know, not just rely on these aids. They need to not be considered as more than what they are. They're called an aid. They're not the end all be all.
Thanks for that. There was one other question that piqued my interest as well, because it wasn't something I'd thought about, and it came from Sam, and I'll read it. With artificial intelligence just starting to come into the construction, one area that's being seen is crane efficiency. It monitors performance and efficiency of the crane driver lifting loads. His question is, where there are multiple cranes on site and you have this technology, do you believe it would be a safety concern as a crane crews try to outperform one another, knowing that they're being tracked by the artificial intelligence, and possibly lead to safety incidents, the complete opposite of why we're trying to bring it in? Any thoughts on that? Any comments?
Yeah, I've seen some pretty perverse outcomes from safety systems. As an industry, we've got to get back to giving training and skills and a career path to learn more and more to the guys in the field. Because when I started in the industry, that's where the skill level was. It wasn't with the engineers per se. Over the last 20 years, people have taken more and more of that planning from the operators. Like I can think of many examples where the crane operator tells, like that example of that franner was on that civil contractor's site that had the latch lock system, and the crane operator told the computer the wrong information on purpose to defeat the safety system. I mean, obviously that's another behaviour that needs to be managed, but the culture that goes around, I can get a computer system that will make robots out of crane operators and it'll be safe. It couldn't be further from the truth. It pushes people in the other direction, is my personal feeling.
Efficiency and productivity, we've got to be careful to create a conflict with safety, because I think sometimes this artificial intelligence space it's really interesting to pontificate on, but it doesn't account for how organic lifting activities are on site. Like Stuart gave a quick example, even when he's talking about load stability, about the plan is to be doing a certain way, and once it gets to site, it's a question of, we don't have the spreader beam, can we use this lifting beam instead? That kind of stuff, I think, needs to get probably better in control before we try to start using artificial intelligence in that space, because so many things are mix of variables that contribute to lifting safely.
Look, it's been a fantastic experience for me coming through and listening to this as well. And some of the information Stuart put forward, I didn't realise there could be such a change in capacity of cranes just based on a serial number as they run off the production line. So it's definitely something I'll be considering myself as it goes. And even those other bits about remembering to look back at the manufacturers for side slope and not just thinking of that 1%. If they're trying to get as much more out, this idea that they'll start doing 0.5 and 0.25 and these sorts of things is something we must consider as we look at them. Look, as a final there, thank you very much, Brandon and Stuart. The presentation was fantastic, and I really appreciate the time and energy you put into putting this forward for us today. As I said, I've learned a lot, and I hope others out there have as well. Would like to sincerely thank you for your presentation and really appreciate the effort you put in. With that, I'd like to say goodbye and sign off for the day and thank everyone. Thank you.